about your project team. The rest of you, please do that. You have till 15th for that. And the second one is about homework 1. I hope you've started your homework. It's due in a week. So, and if you've never done this before, it may take time. So please start soon if you haven't already. Are there any questions about the homework? Yes?
Do you have any tips for applying those Voronoi diagrams, particularly the Manhattan one? That's kind of an algorithm.
Right, so that's a good question. Let me repeat the question. Questions about any suggestions for plotting Voronoi, especially for Manhattan. And so I don't want you to be agonizing over this. This is supposed to be an easy question, first of all. So don't overthink it. That said, Voronoi for Manhattan, there is a slightly not so obvious thing which I'm not going to say right now, but I want you to explore this idea. The general way to answer this kind of a question is to think about the set of, so one definition of the Voronoi, the boundaries, it consists of all points which are equidistant from two data points. So you need to find a point x comma y, and define its distance according to the measure that you have, and look for the locus of those points that are where this distance from one to another is the same. That's easier said than done. So my suggestion would be just pick some points and explore by doing that, rather than trying to apply an algorithm. There are algorithms for this, but I would consider that to be somewhat out of the scope. So pick test points, and once you get some sort of a diagram, very quickly you'll see that there is an obvious answer by doing this method. Then once you get the obvious answer, convince yourself that it's right. The Manhattan may have a bit of a trick. I'm not going to say it will or will not. It may have a trick. So, is that, I don't want to give away the answer, but does that answer your question? Okay. Any other questions about homework 1? Yes.
So I kind of had a question. I walked in a little bit late with mentioned similar, and I don't know if this is kind of maybe digging a little bit too deep, but when you do the Voronoi diagram for the L1, is it possible that you can, like with L2, you have the nice polytopes and stuff.
Yes.
With L1, can you have regions where?
Yes, you're right.
Where it's
you will.
A bunch of equidistant points?
Absolutely.
Okay.
Yes, that's the trick in this question.
Okay.
All right. If there are no other questions, let's go ahead. Today we're going to start a topic that I think will occupy us for a large part of the semester, and this is the first introduction to this family of models, this family of functions, this hypothesis space, if you will, called linear models. Linear models are one of the more dominant classes of functions that are used, and it has very interesting geometric interpretations. It comes with interesting algorithms, and studying linear models will let us explore a large part of machine learning. And so this lecture, I don't know why, it's chapter 5, let's say, is going to lead us into classes of algorithms. It will lead us into an exploration of this question of what does learning mean, and we'll see multiple answers to the same question, and each of them will give us new algorithms for learning linear models. So let's get started. Before we start, I just want to just remind you of where we are. We are still doing supervised learning. We'll be doing supervised learning for quite some time. And in the first class, we looked at instances, concepts, and hypotheses. And learning is simply search for functions, search over the hypothesis space. More specifically, the cartoon picture looks like this. You are given some training set, labeled examples. These get thrown into a learning algorithm, and the learning algorithm spits out a function, a hypothesis. Sometimes I'll call it a model. let's call it H. After learning is done, there's this deployment phase when this algorithm will be let loose in the wild. It will be given new examples and it can produce a prediction. In particular, we looked at two learning algorithms, two learning algorithms, one for decision trees and one which is kind of a fake algorithm because it's so simple, the nearest neighbors classifier. And we also looked at some rather important machine learning concepts. One is overfitting, and overfitting versus underfitting, and I didn't talk about underfitting much, but we certainly saw examples of overfitting. The other one that we saw in the last lecture was the curse of dimensionality, which is this intuition that if you go into high dimensional spaces, just be careful when you start reasoning about distances. And an underlying assumption we made through all of this was that you can think of features as high dimensional vectors. Now, I'm fairly certain that some of you are not very comfortable with the idea of high dimensional vectors, but I would suggest you get comfortable soon because we'll be doing a lot of that. Any questions? At some point, I'm maybe going to start pointing to people and ask them to ask questions. Yes?
What's a good way we can become more comfortable, like what exercise we can go through to become more comfortable with high-dimensional spaces?
By working with it. So one thing that I found useful myself was very often geometry is useful with this. I try to picturize things in 2 or 3 dimensions because that's what I can do, and use geometry to give me some intuition but not believe it completely. Algebra is the final say. The other thing that becomes very, very useful is to think about most of the functions that we'll be looking at, in particular linear, are literally just lines or planes. So I'll give some geometric intuition. I found that to be the most useful thing. It's useful to also think about, be familiar with vector calculus. We'll be taking derivatives of functions that go from n-dimensional space, that map n-dimensional spaces to the reals, and we'll be taking derivatives of this all the time. And it's important that you should be comfortable with that. And the only way to do that is to,
Just do it.
yeah, the same lesson that you have for calculus. How do you get comfortable with calculus? So really, that's not an answer, but just saying it's not scary. Okay, so let me give you an overview of at least this lecture. We'll be looking at linear classifiers, and we'll see how linear classifiers are a very expressive hypothesis space. They cover a lot of functions that we might be interested in. And I'm going to take a detour from classification to regression just to introduce this idea of learning as optimization. And I'm going to step through linear regression. Some of you might have seen it before, but it's good to see it again. And I'll end today's lecture with a survey of different algorithms for learning linear classifiers. And these will be algorithms that you've probably at least heard of. Things like neural networks or naive Bayes classifier and those things. So let's start with linear classifiers. If you remember in the first or the second lecture, I had this slide where I said that learning seems impossible because it's search over functions and there are just way too many functions. So even in the Boolean case, if I have 4 inputs and I give you 7 labeled examples, there are still 16 minus 7, that's 9 outputs that are unspecified, and an adversary can potentially label those examples in a way that makes learning impossible. And there was a combinatorial argument that I presented, which said that there are, in this case, 2 power 16 functions that might exist in the space, 2 power n, and a large fraction of them are still a significant fraction of them would agree with the labeled examples, which means that we have no way of disambiguating. So the argument I made that in that lecture was that it seems that learning is really impossible. But then, what was the answer here? What was the one way of not running into this combinatorial problem?
Restrict the hypothesis.
Restricting the hypothesis space. Who said that you have to search over this set of 2 power 16 functions? Up front, before your learning starts, you declare that you're going to search only over a subset of them because you believe that whatever concept generated this function was not picking a function randomly from the space. So the hypothesis space is not the set of all functions that exist, but it's a set of functions that the learning algorithm considers. And one of the most important tricks is to realize that learning is impossible without restricting the hypothesis space. Generalization is helped if the number of functions you search is smaller. So in Boolean land, there are some named functions. You can say that you are only going to search over the class of all Boolean conjunctions. Only functions that are disjunctions, for example, or functions that are m of n classifiers. So you have millions of features, you declare upfront that there are these n features that are interesting and only m of them, or only n features are interesting, and if m of them are true, you will declare the output to be true. That's the class of functions that are m of n. And you're looking at m of n functions in your homework, so you must know everything about it. Another such hypothesis space is the space of linear functions. And linear functions are very interesting because they have some very cool geometric properties, some very interesting properties with respect to optimization, and let's see why. One example. So let's say you have some training examples. I want to separate the set of blue points from the set of red triangles, and I want you to tell me which of these classifiers is better. I can have a curve that perfectly separates the data, or I can have a line.
The line is
Why? Other than the fact that we are talking about linear models.
Avoid noise.
So,
The line can avoid noise.
the line can avoid noise.
You risk overfitting your data. When
You're
you do
basically
that.
overfitting your data. So we don't know for sure. Oh, by the way, just when I draw these things, I mean that you're separating these. One side is blue, one side is red. If you're fitting the line, if you're fitting the data perfectly, it's possible that you might be fitting the noise in the data. Another way of thinking about the same thing is the number of lines there are. Actually, the number of how many lines are there in the space? How many lines exist? Infinite. How many curves exist? Infinite. But somehow the set of curves seems like a larger set than the set of lines. The search space is restricted, and we will formally quantify this argument later. So the set of lines is a simpler hypothesis space. And actually a similar sort of an argument shows up in this is for classification, similar argument shows up in regression. If you have a set of points, I can either draw a curve that perfectly fits the points, or I could use linear regression and say that the points that don't lie on the line, there's some noise that's just pushing them away. The true data, the true f of x was actually a line, and the observations are corrupted by noise. So this shows up in regression land as well, and the argument for using linear regression is similar. You use simpler functions to avoid overfitting. Let's define, before I get into defining linear classifiers, any questions about this? Yes?
So you're talking about overfitting here, is it that, so if we make an assumption that the data is actually free of noise, do we still have that fear of overfitting?
No. If you make an assumption that there's no noise, maybe that's what the data is, but I can't think of any data that's free of noise. We have to, I mean, most of the time, we don't even know what the noise looks like. Yes?
If I'm not mistaken, noise can be, when you say noise, that could be anything. It could be mismeasurement, or it could be other factors that we're not concerned about.
Yes, yes. Noise could be something that's affecting the features. So the feature should have been true, or the feature value should be, I don't know, 6 feet 3 inches, but it's accidentally written as 3 feet 6 inches. Or it could be noise in the label. This email should have been marked spam, but accidentally it's marked as not spam. It could be anything. And it's often outside our control. Actually, most of these things are outside our control, but noise particularly is. Yes?
So in your seminar, you made a point that if you have infinite amount of data, if you are overfitting, then basically you are getting a function.
Yes.
So is it does linear classifier work for a huge amount of data, or
Hold on to that question and keep that question for another 2 lectures. And we'll come back to this. The short answer is we can get some guarantees for linear classifiers in terms of the separability of the data. So we need some functions that are just not linearly separable. If they are not, we can't separate them. So hold on to that question, and maybe at the end of this class you will probably get the answer yourself. So let me give a terse definition of linear classifiers, but explore this idea a little bit more as we go along. For most of the rest of this class, so semester even, I'll assume that inputs are n-dimensional vectors. Sometimes I'll use d for the dimensionality, and it should be obvious from the slide whether that I'm referring to the dimensionality. So inputs are vectors in some large dimensional space, and for classification the label is one of a discrete set. It can be plus minus, spam, not spam, and so on. A linear threshold unit is a function that's defined using 2 parameters. There's something called, and these are called the weight vector or just parameters, and I'll use the symbol. I'll use W for the weight vector and B for a bias, and it's defined the following way. So if you have an example, a new example comes in, x here, you take the dot product of x with the weight vector, with W, add the bias, you get a number, you threshold that number. If that number is positive, the output is positive. If that number is negative, the output is negative. If you're not comfortable with dot products, it's equivalent to saying the output is the sine of Wi xi plus bias. Here x's are inputs, and W and B completely define the classifier. And this is called a linear threshold unit. B is called the bias, W is called are called the weights. Together sometimes they are just called weights. And let's look at the geometry of this. Again, and this is how I like to visualize linear classifiers. You have some space, x comma y, or x1, x2, and you have some features x1, x2, and your points, your inputs are points in the space, something like this. A linear classifier basically slices the space into 2 parts. Remember that it's just, in this case, you have 2 dimensions. It's bias plus W1 x1 plus W2 x2. Take the sign of that. And from the geometric perspective, what you're doing is you're drawing a line in the space, and you're proclaiming that one side of it is positive. This is so weird. You're deciding that one side is positive and the other side is negative, and that gives you your classifier. Notice that every point in the space exists on one or the other side, right? Except points on the line. Questions? And questions about the geometry here?
When you say the sign SG, are you talking about mathematical sign like SIN? Is that the same thing?
No, I'm talking about the signum function. Sign is it greater than 0 or not? It's a threshold.
Gotcha.
Yes.
B, W1 and W2 are assigned by the training algorithm?
Yes, the job of learning is to find B, W1 and W2.
In such a way that we could separate them.
Exactly. The job of learning, and there are dozens of learning algorithms, all of which compete to find the best one, and each of them they all have their pros and cons, but they all find the same thing, B, W1 and W2. And a couple of other things. Notice that W1 and W2 are a vector. W1 W2 together form a vector, and if you're not familiar with vectors, it's basically a point in some n-dimensional space. You can think of it as a direction, and that's really what. Oh, okay, that's this thing here. And the B moves the line in parallel. So this is this line here is for some B, and then if a parallel line will have another B. So this could be B prime. And what is important is we only care about the sign of this score, B plus W dot X. We don't care about the actual value of the score. And this becomes important in defining learning algorithms. And the other thing you should remember is all linear threshold units, in 2 dimensions they define a line, in n dimensions they define a hyperplane, and all they do is you find this plane that slices the space into 2 parts. And automatically you get one part that you will call positive and the other part you will call it negative. Yes?
Is your weight vector normalized?
Does it have to be? That's a very good question. Keep this point in mind. Does it have to be normalized? If it's normalized, will it change which side of the line it falls on?
Might make your math easier.
Possibly, or not. In fact, that's a good question. Right now I'm going to say it does not have to be normalized.
For points very close to the line, it may be there may be some kind of ambiguity.
No, because if either a point is on one side or the other, right? Let's assume that on the line is the positive side. So either a point is on one side or the other, which means that the magnitude does not matter. Because, let's work out this math. So you have W dot, I'll use W dot X, W transpose X, they all mean the same thing. W dot X plus bias. A normalization would just divide this by some, say, something like this, which is a positive number. The sign of this whole thing is the same as sign of this thing, because you're dividing by a positive number. But actually the magnitude of this W becomes important for certain learning algorithms. Other questions? These are good questions. Yes?
How do we want to choose our bias?
The learning algorithm has to decide both the bias and the weights. And in fact, maybe in about 10 minutes, I'll point out that the bias is just another weight. And I'll fold it into W and we'll stop worrying about it very soon. So all I have done here is I've defined a class of functions. And I'm just saying that these are an interesting class of functions that has seen a lot of work. Now the question is, why? Why are these functions more interesting than others? And in particular, what classes of Boolean functions, for example, do linear classifiers define? It turns out that these functions are extremely expressive. Many Boolean functions that you know and love are actually linear functions. Not all, and we'll look at some examples. Just as a reminder, remember that you can represent any Boolean function with a decision tree. And you're doing that in your homework as well. For linear classifiers, you can't represent any linear function, any Boolean function as using a linear classifier, but many. So we are restricting the set of functions that we are considering to a large expressive set but not complete. So let's look at some examples. Conjunctions. Conjunctions are, in this case, I'm defining, think of a function that's a conjunction of three booleans, x1 and x2 and x3. And this is equivalent, I'm going to claim that this is equivalent to the boolean to the linear threshold unit, that's this one, x1 plus x2 plus x3 is greater than or equal to 3. And I'll use, as a convention, I'll use 1 to denote true, and either 0 or -1 to denote false. It's obvious from the slide or from the context what is true and false here. So just to remind you, the conjunction is this function that says that which assigns an output value of 1 only when all the inputs are 1. And this is a linearly separable function. Why? Because consider this, this function. Let's look at the value of that function. Or equivalently, I can look at the sign of this thing, x1 plus x2 plus x3 minus 3. And the proof is fairly simple in this case because I can just enumerate all possible options, and x1 plus x2 plus x3 will be more than 3 or greater than or equal to 3 only when all three of them are true, which is basically the last line here. So conjunctions are linearly separable, and this is a special conjunction. It's called a monotone conjunction because x1, x2 and x3, none of them are negated. Even if any of them are negated, this function is linearly separable. x1 and x2 and not x3, this is a symbol for not, and not x3 is also linearly separable according to a different function. And exercise number 1 for you is to convince yourself this is true by just enumerating all 8 options in this case. Similar sort of a claim can be made for disjunctions. Simple disjunctions, basically monotone disjunctions or disjunctions which have negations, are all linearly separable. And disjunctions are functions that are saying x1 or x2 or x3. And another exercise, take the same function, replace all the and with or, and try to figure out a boolean a linear threshold unit that represents the same function. Any questions about conjunctions and disjunctions? And this, by the way, this is proof by example, but this statement can be generalized and it's true for all conjunctions and disjunctions. Questions? And I've decided to go deliberately slow today because either this must be blindingly obvious or impossible to understand. So, and if you're seeing it for the first time, it might be a little confusing. Yes?
So there's a one-to-one correspondence between the conjunction and any combination of conjunction, disjunction, and this linear...
No, actually it's not one-to-one. It's one-to-many. And that's interesting because x1 and x2 and x3, let's take this conjunction. I'm going to write another linear threshold unit, which is sine of 2x1 plus my x's look like it's the same line, right? That's okay. What if I have conjunctions are okay? Well, let's take disjunctions. So first of all, this is the same line as the one before.
Yeah.
But in general, I can create other linear threshold units by basically moving it by epsilon. For conjunctions, it's a bit more tricky. For disjunctions, actually, it's much easier. In fact, even for conjunctions, I can say greater than 2.5. It's another line which has the same, because do you see that it will be the same function, or same Boolean function? Because when we move to the space of real, there's a little bit more wiggle room. Actually, there's a lot more wiggle room. Other questions? Yes.
So if you have multiple groups of data, can you use it to make the Voronoi diagrams? Like if you go back to the slide before, you just have one single line. Let's say you had a third cluster. You could sort of fork it so long as they're...
Right. So this is actually the problem of multi-class classification. And there are learning algorithms which tries to learn these things, but often you can't get arbitrary Voronoi diagrams. There's this idea of linear separability for multiple classes, which is a strict subset of all the set of all functions. So the simple answer to that question is the following. Nearest neighbors can represent any function. Linear classifiers don't represent any function, which means there must be functions which are not linearly separable. So, no. Okay, so this is one class of functions, but life is not all conjunctions and disjunctions. There are other things also. In particular, there are these M of n functions. I'm not saying that life is just conjunctions, disjunctions, and M of n, but M of n rules are, just to remind you, you have many features, and somebody has decided there are these n special features which are the only relevant features, and the function takes the value true if any m of them, if at least m of them are true. So, for example, if you have 5 Boolean features, x1 through x5, and I have decided that the 3 special features that are relevant here are x1, x2, and x3, and I'm defining an m of n, in this case a 2 of 3 function, as at least 2 of these 3 features should be true for the output to be true. Now the question to you is, can you think of a linear threshold unit that represents the same function? Yes?
x1 plus x2 plus x3 should be greater than 2, greater than equal to 2.
At least 2.
Yeah.
So x1 plus x2 plus x3, if it is more than 2, then these 2 things will be the same. Yeah?
I'm a little confused with the m of n function. If we're given the function, then what are we searching for?
No, if the true function is that, and we are searching for that function instead of, so the true function is an m of n function, but we don't know it. Instead, we are deploying linear classifiers to find that function. And the question is there a linear classifier? Does that function exist in this class? And the answer is yes, because it's the same as this linear threshold unit. Other questions? So this is good. There are some interesting functions. So the set of linearly separable functions are not uninteresting, which is a promising sign. But unfortunately, not all functions are linearly separable. The classic example of this is the parity function. The parity function might look something like this. You might have seen this as XOR, for example. You cannot draw a line that separates out the pluses and minuses here. You can try if you want, but you can't. And in fact, this was such an important observation that it almost killed research in neural networks for a decade after a book stating this point was published in 1969. So the parity function is not linearly separable. In fact, XOR is like the prototypical example for many things that are impossible. This is just one function, and in the Boolean world, XOR is I hope you've seen XOR at some other capacity. Another way of thinking of parity is the function that says true if there are an even number of trues in the input, and it says false otherwise. That's not linearly separable. And in general, arbitrary Boolean functions are not linearly separable if you have some conjunctive or disjunctive terms, a mixture of conjunctive and disjunctive terms, like this thing here. So that means we are severely restricted in the class of functions that we can express. But all is not lost. It turns out even these functions can be made linear with a trick that is so important that I'm going to repeat this multiple times through the semester. So, just as an example, here are some points, here are a grouping of points that are not linearly separable in one dimension. So their points exist on this line, and I cannot find a one-dimensional line that separates this thing. What's a one-dimensional line? A point. You cannot find a single point here and say that everything to the left is blue and everything to the right is red. Obviously. And the trick here is, who said that you have to live in this space? You can transform your examples by deterministically taking these examples and converting them to a new representation where it might make it linearly separable. And the answer is something called blowing up the feature space. In this case, the transformation that I'm going to do is to represent every point x here, move it to 2 dimensions by giving this additional feature x comma x squared. And that will give you something like this. Now clearly it's linearly separable. I can draw a line here that is separating the pluses and the dots. Now, just to make this point clearer, every point in the original data was transformed to this new space. Original points lived on the line. Now with this transformation, I have taken these points from the line to the plane. And on this plane, I can now separate the positives and the negatives. Does this make sense? Questions? I see a
So is
hesitant
this a way
hand.
that you could sort of do like a like if you projected it back down, you basically chose 2 points now to separate the pluses from the dots.
Right.
So you kind of have like a multi.
Or you have a curve. You have a curve that lives in a higher dimensional space but intersects with the line only in 2 points.
Yeah.
Right. Instead of that, you're now moving the points to the new space and now drawing hyperplanes in that new space. Now this is people often have trouble with this because then the question comes up, how do I know what the right transformation is? But you have a different question.
Yeah, related question. Question is there a formal proof that suggests that even though we apply this transformation, we are actually not playing with the original function in terms of distorting it?
We are distorting it. Another way of thinking about this is polynomials. We are using polynomials to separate out the data. And if you have a finite number of points, you can always find a polynomial that separates the data. Right? So the risk that you run with doing these kinds of wild transformations is you might overfit. Because you'll always find a polynomial. And who said that the degree of the polynomial, what the degree of the polynomial could be? In the limit, it could be infinite. So you can always fit any data using these kinds of, if you try out all possible transformations.
With that in mind, isn't the parity?
Yes,
Okay.
that's an excellent question. In fact, so let me complete your question for you in the form of an exercise. What I want you to do is invent a feature transformation such that the XOR function is linearly separable. So consider the case where you have 2 inputs, x1, x2, and the output, the true function that is hidden from us, is x1 XOR x2. And what I want you to do is create a function that maps x1, x2 to some new space where you can just draw a plane to separate it out. And the hint that I want to give you is that you should think you can't do it in 2 dimensions. You need to introduce an additional dimension. Think quadratic functions. I'll come back to this in the next class because I do want you to think about this. And maybe in the next lecture, some of you can tell me what the answer is.
So, like what you were showing was you transformed the data into a new space so that you could draw a line to separate it. But like you could also imagine the data stays in its space, and then you drew like a
curve. Yeah, it's the same thing. The nice thing about being able to draw, yeah, in fact, that's totally right. The nice thing about drawing a line in the new space is that we only need to study algorithms for learning lines. Right? And move the data around so that you can still throw it at the same learning algorithms. Of course, and also we can analyze these algorithms and introduce the dimensionality of the space as a parameter that we'll use to analyze. And then it will become fairly obvious that throwing in arbitrary transformations to high dimensions is not necessarily a good thing. Yes?
So, both the transformation for the one-dimensional space and this one that you're suggesting is based on the fact that we already know what the function is.
Yes.
And
yes.
So how is this useful in a situation where you don't know what the function is? Do you make a guess at what you think the function is going to be, and so you make a transform that would fit that if that were the case?
Let's pretend that we only want to try out different polynomials. Okay? Let's pretend that we are going to try out polynomials of size. Huh?
As transforms?
As transforms, for now. And let's say that we want to try out polynomials of degree 1, which is just linear, 2 and 3. How do you know what's a good polynomial? You have only your training set. What would be a good method to determine what's a good transformation? You have only your training data. It's a hyperparameter. How do you find good hyperparameters? You cross-validate. And you do the same. You try out different things, use cross-validation to see what fits, what has least cross-validation error.
How does linear classifier work when there are more than 2 labels?
That is the problem of multi-class classification. We have an entire lecture devoted to that. In general, the way it works is you have to basically transform this pair of input comma output to a new space, and then say that is this input output a good or not. So you create a fake binary classification task. There are at least 3 popular ways of reducing multi-class to binary. You basically use the same algorithms that we have for binary and reduce the problem to this thing. And we'll be looking at this method, probably that might be one of the last lectures of the semester. Was there a question? Did you have a question? Okay, so this is I'm still making a strong assumption. What am I ignoring in all these things?
That all the data is correct.
What did he say?
That all the data is correct.
That all the data is correct. I'm ignoring the fact that there may be noise. It turns out that a lot of times we also have something that I like to call almost linearly separable data. Let's say you have these examples and you may have some noise. Now this data is not linearly separable, I know because I put the points there. But you can draw a line that is almost right. It only makes 2 mistakes. Is that good enough? How do you know how much noise to allow for? And often that becomes a parameter to the learning algorithm. Either I can allow noise or I can do this transformation to some very high dimensional space such that this gets classified correctly. So would I be better off just sticking with the noise or doing the transformation? So, and we'll see how this works in our favor when we come to support vector machines. Okay, so just to summarize, linear classifiers are a very expressive class of functions because many functions are linear. Many functions can be made linear with this kind of a feature transformation trick by blowing up the feature transformation. And very often we'll be able to find linear functions because things that are not linearly separable can be explained away as noise. Any questions about, I do want you to remember that not all functions are linearly separable, and sometimes you have to do this feature transformation or something because You just don't have the, your space just does not have the capacity to support the labels. Yes?
So I apologize, this actually goes back a few slides, but so when you took that x to x comma x squared, so you basically expanded the space, you ended up drawing a horizontal line, which although you mapped it to a two-dimensional space, you then, well, like, you could, like, say if you had different points, it could have been a horizontal line. Then you really need to...
Well, this is just a cartoon example. I'll give you another, let me give you another data.
My point is, though, if only x squared is the only relevant term, then can we just map it to a different one-dimensional space?
Actually, in this case, x squared would have worked. For this particular data set, x squared would have worked, just x squared. So it does not have to go to a higher dimensional data. So that's a very good observation. I want you guys to convince yourself that the transformation from x just to x squared would have been sufficient for this data set. But in general, the transformation goes to a different vector space. It does not have to be a higher space.
So like similarly then for XOR, we could just map it to x1 minus x2 for the absolute value.
Yeah, but absolute value is a nonlinear transformation. Yeah, sure. Yes. I mean, the transformation does not always have to be to a higher dimensional space.
To any
yes.
space. Okay.
Yes.
The transformation cannot be linear, right?
If it is linear, then it won't work. If it's linear, then the original thing would have worked, because that would have been folded into the original function. So this is another opportunity for me to remind you that if you're feeling that this analysis through geometry is difficult, go back and just refresh.
I have a question. So if you map x to x squared, how can you find if the x squared larger than something, but you cannot find the original x? I mean, if x is positive or negative, you cannot find, because the x squared is the same value, you cannot find the original x. So how can you separate?
The way we do this is we get the new input. So think of how the classifier works. You get a new data point, x, some point here. It's negative in this case. You map it to x squared, which will go somewhere here, and you draw a threshold. And then the label for this new point, you will map it back to the, remember that label, that point.
Are there situations in which, like, you're not able to project the linear transformation back into the original space, so that you'd be able to label, but you wouldn't be able to generate new samples?
Well, we never generate new samples, right? We are given an example. We have that example. We're not going to throw it away. And we are always going to define the output that we produce as the label for that example. You do some processing and use some transformations, but you still have that example. You apply, get a label for this processed version of that example, and that label is still the label for the input that you have. You don't throw it away.
Yeah, okay.
So what's the fundamental difference between that feature transformation and using a piecewise linear? I mean, why shouldn't I just go for a piecewise linear?
The set of functions that are piecewise linear is definitely more expressive than linear functions, right? The reason linear models are interesting is because we have many algorithms that are defined for linear models and come with guarantees. Guarantees of learnability, guarantees that that they will be found easily.
Even after that feature transformation?
The feature transformation is just to point out that even functions that are not linear are linear in a different space. Let's move along. So the one other point I wanted to make, which is something that I think one of you asked, was about this bias term. So the question was, why is the bias term needed? Why bother? Because you have this data. What would happen, and let's say you had this original classifier that we saw before. What would happen if I do not have that bias term? 1%.
Go through the origin.
It has to go through the origin. If b is 0, then we are only restricting ourselves to functions that go through the origin, which means we are not allowing ourselves the liberty to find all possible functions. Just by adding this one bias feature, we are increasing the expressivity of our classifier. Otherwise, by not adding bias, you are only allowing yourself to search for functions that go through the origin. By introducing the bias, suddenly you allow yourself to search space of all possible functions, including this one, for example, which you did not give the liberty to your, which you did not allow your learning algorithm to explore before. That said, it's very easy to kind of hide the bias with one little trick. So the first trick that you saw today was this feature transformation trick. The second one is more of a just a convenience, a notational trick, which is we can stop writing b at every point, and I'm going to do that after this slide. Remember that the prediction that we have is sine of w dot x plus b, right? This thing here. What I will do is, given an example x, which is some vector, looks like this. X is some vector. It's 1, 2, some n-dimensional vector. I'm going to deterministically add a new feature called whose value is a constant, always 1. 1, x1. And I'm going to rewrite my original weight vector and bias together. My original weight vector looks like this: w1, w2, wn. I'm going to map it to b, w1, wn. So I want you to convince yourself that w transpose x, which is sigma, well, the dot product of this guy and this guy plus b is simply the same as the dot product of this and this.
Would it be better idea to just let b to be taken care of by the feature transform?
This is another feature transformation. And this is a notational trick, nothing more than that. So I'm introducing, what this effectively does is it increases dimensionality by 1, adds a feature whose value is always 1, and now the prediction is just a sign of w prime, which is w comma b, transpose x, which is x comma 1. In this new space, because there is no bias in new space, in the n plus 1 dimensional space, this hyperplane w prime goes through the origin. But because there is a constant feature, there is a bias term. And this is just notational convenience, does not change the algebra at all, it just makes life a lot easier because you don't have to keep carrying this b around, and it makes the math simpler. So sometimes I'll have b in my slides, in notes or whatever. Very often I won't. But remember that there's always a bias, because if you do not have the bias term, you're only restricting yourself to weight vectors, to lines that go through the origin. In fact, this is a crucial thing to remember. People who've been working in the field for many, many years often forget this, and suddenly classifier performance drops from, I don't know, 80 or 90% to a 60%. And it's a very, very painful bug to diagnose. So always assume there's a bias feature, or always, if you do not explicitly add bias, you have to add a bias feature. I tend to always have a bias feature either way, just to make sure. Any questions about this notational trick? Okay, take a look at it again and come back with questions. But I do have some exercises, which is just to remind you, one of the slides before, the number may be wrong, asked you to, just as a reminder, I want you to try these things at home, represent a disjunction as a linear threshold unit and convince yourself that the XOR function can be classified using, can be made linear in a different space. These are useful things just to kind of make yourself comfortable with this sort of this family of models. So let's take a detour. Let's go from classification to regression. And I'm going to talk about this method called least mean squares or least squares regression. And let's use this tiny little example. Say you want to predict the mileage of a car and you have only two features. You have the weight of the car and its age. And you have 4 example points. So we have to predict this number. We want a function that can predict mileage given x1 and x2. It's not a classification problem because the output of a classifier is either true or false. Here we are predicting a real number, so first of all, it's a regression problem. And in particular, we'll be looking at linear regression, which is simply predicting these output values as pretending that the output is a linear function of the input. So you have, let's say, in other words, I'm going to pretend that the mileage here is simply the dot product of some w and x plus a bias, w0 plus w1x1 plus w2x2. And now the job of learning is rather simple. The job of learning is to find the best w0, w1 and w2 given the training data. And once learning is done, we have these weights, we can then use it to predict the mileage given these two observed features, the age and the weight. These, just to remind you, these weights, w0, w1 and w2 are the parameters of this problem. They're also called the weights. I'll keep using the word weight vector a lot. And together they form a 3-dimensional vector, which is something like this. And your input is a 3-dimensional vector which is 1, which is the bias term, x1 and x2. So the job of learning is to find the weight vector. And the strategy goes like this. Let me formalize this before talking about the learning algorithm. Inputs are in general some d-dimensional vectors, and the output is a real number. And our goal is to use a training set. Someone has gone out there and collected labeled data points. So we have a finite set of examples. We have m examples which are simply pairs of x, y. And our job is to use this labeled training set to find a function f, which is simply a linear function of the inputs. And just reminding you that there's one feature which will always be 1, the bias feature. So our job is just to find this weight vector w. It's a d-dimensional vector. And linear regression shows up everywhere. Some of you may have seen it before, some of you may not. But it effectively lets us find real valued predictors. So, for example, you may be given a bunch of points. In this case, let's say it's 1-dimensional input. You have just one x1 and you want to predict, you have one x1, you want to predict a y. And you will find a line such that looks like w1 plus w2x. This is a mess. Something like this. And when a new example comes in, you try to predict.
Can I go back to the previous? So is x1, x2, all these are features or data points of a particular feature?
x1, think of right, that's another notation. I use boldface to denote vectors. So x1, x2 would be something like this, one row in this table. So all the features of one example. So in the one-dimensional case, linear regression is simply finding a line. You can do this. It turns out that this function is not our only choice. A similar sort of a decision comes up. Do we find a line? Do we find a curve? If you find a line, then there are fewer lines in some sense, so the learning might be easier. But sometimes curves help us better, and so on. You can, just as another toy example, you can have two-dimensional points, and you can predict using a plane. So the real question now is, I said, given a set of training examples, you need to find the best weight vector, or the best line or the plane that fits the data. Now the question is, how do we know what's the best? What does best mean? Sorry? With the lowest variance. I don't know what variance means. It's something much simpler.
The best is the one with the least mistakes.
The one that makes the least mistake. What's a mistake?
A misprediction.
A misprediction. In this case, in regression, I can define misprediction as, or occasionally I'll use the word cost, is simply the difference between the true label and the predicted output. You're given an example xi, yi. Yi is the label for this particular data point, and I'm going to define the mistake as the absolute difference. Because it's regression, we can just use difference. And for a particular weight vector, I can define its cost, total cost over the entire training set, as simply the sum of all the mistakes. Because the math works out nicer, absolute values are kind of annoying, we'll use sum of squared mistakes. So we go over all the training points. For one particular W, you find what is the mistake that this W makes on every example, and in this case I'm going to use a squared error. Add all the errors up, and this is how bad this vector is. And a natural strategy for learning is to find the W that is least bad. Right? So this is called this mean, or this is the sum of squared errors. And as I said, the goal of learning, I can now try to formalize learning as find a W that minimizes this quantity. And I'll use J of W for this quantity. Yes?
You also apply the concept of cross-validation here. I mean, like you have over, it looks like if you want to apply all of the samples you have, it's the same as over.
No. So let's think about what cross-validation does here. I want to search over all W. Right? Now W is in the space of all reals, real points in n dimensions. Cross-validation requires you to get one W, test it, and get another W, test it, and keep doing that. But it's, by definition, you can only test a finite number of objects. Right? What we want to do is search over the entire real space.
Yes, but I mean the way that we do, make them into chunks and then you find W for.
Yeah, but the nice thing about this is I don't have to do that. I can actually solve this analytically. I can define an algorithm that uses the fact that we are in real space. And we'll do that right now. Yes?
What's the 1/2?
What's the 1/2? It's just there to make the calculus work out better. That's really the real reason. That's the reason. So this gives us this idea here of minimizing this square error for regression is also called, very creatively, least mean squares regression. You minimize squared error, but the mean of it. And this presents, now this gives us this a big hammer that we can now swing at it, which is the theory of optimization. Problems like these is our bread and butter for optimization. So we can now throw in all the algorithms and the math that we know, or we would learn now, for optimization, and use that to define learning algorithms. In general, this is a common strategy for learning where first you define something that is called loss or cost, something that you don't like. In this case, the difference. You add up the differences across the entire training set and you define learning as finding the minimum of that sum. Find the weight vector that minimizes loss. And a very popular algorithm for this whole thing is gradient descent. Just for this particular objective, it turns out there is an analytical answer to this. You can just literally work out the answer for this problem algebraically. There is no need for an algorithm, but let's try to invent an algorithm here. How many people have seen gradient descent before? About half the class, about a third. So, gradient descent is a general strategy for minimizing functions, and the recipe looks like this. You have some function, and I'm drawing this function on the slide here. This is a function of w, right? The cost is a function of w. You want to find the w that minimizes everything. So you have a function of w. This is to minimize. What you do is you have no idea. You just find something, yes, and you look at the gradient of this function at the point that you've guessed. Now the gradient is simply the derivative of the function, and it's the direction in which this function grows the maximum, grows the fastest. You know the direction in which the function grows the fastest, but you want to go to the minimum. What do? The function is increasing this way, and I don't like this, so I go the other way. That's it. So you update your w. Once you get this gradient, you update your w, you find a new point. You just go back in the reverse direction of the gradient. Keep doing that till you come to some minimum. You iterate until this whole thing converges to the bottom. And the way I like to visualize this is, say I have a bowl and I put a drop of water somewhere, it will keep going down till it comes to the bottom and settle down. And think of these points as the intermediate positions of that drop. Yes.
Is this J guaranteed not to change? Is it going to have multiple minima?
You've seen this before. So this function that I wrote in the previous slide does not have multiple minima. In general, we have no such guarantees. In general, gradient descent will take you to local minimum.
In the top right corner equation,
Yes.
xi and wri are scalars, right?
No, x's and w's are vectors. That's why I'm taking a transpose here.
So you are adding two multiple vectors.
Which one?
You are adding from 1 to n.
This one? This term here?
Yeah, so you are adding.
So let's go back to let's create some room. So I have a marker that doesn't always work. Let me go to the previous slide where this thing. So W is a vector, an n-dimensional vector. X is your input. W dot x is a real number. Y minus W dot x is a real number. I take its square.
So what is I?
I is indexing over training examples.
Oh.
Yes. So this is.
It's not the m dimension.
No. M is the number of training examples we have. Yes. That's another point that I should mention. Very quickly we'll be inundated with subscripts and superscripts. So if you lose track, just ask. Yes.
You should also be dividing this by total number of training.
Yes, that's how I get the average, but it's a constant. So if I'm minimizing, to get the real average, I need to divide this whole thing by m. But m, the function that minimizes this fraction is also the function that minimizes the sum. And if you divide by m, that's why you get the mean square part, the mean part of the mean square. So this is a general strategy for gradient descent, and let's try to instantiate this idea for the objective that we have. The algorithm looks like this. You initialize some W0, and when I say initialize W0, this is some vector in n-dimensional space. It's a point in space, yes.
For this, is there any algorithm that's usually used, like Newton's method or the secant method or something for minimizing it, or?
No, the gradient method is the simplest one. You could use Newton's in the Newton's method or some sort of a secant sort of method, but recent results in the machine learning world point out that gradient or variants of gradient descent do really well. In particular, something called stochastic gradient descent often does spectacularly well. You don't need second order methods like Newton, or the secant method is also called, another famous algorithm is LBFGS, which is a secant method, and we don't need that. In fact, I won't even be covering that in class, because that is a wrinkle that it seems we don't necessarily need. I'm not saying that it's not a good algorithm, but simple algorithm seems to work pretty well. So to do gradient descent, what you'll do for least mean square, you find an initial point and you iterate. At every step, you compute the gradient of your objective function, j of w, at that point, and update your weight vector in the negative direction of the objective, so of the gradient. So given a w at a point wt, when your estimate of the weight vector is wt, you find its gradient, that nabla j, and you just take a negative, you go in the negative, you go in the opposite direction of the gradient. How far should you take a step? And that is determined by this thing called R, which is the learning rate. And if you're going down the bowl and you take a huge step, you can just overshoot the minimum. So very often the theorems assume that the learning rate keeps decreasing as learning progresses. For now, let's pretend it's a tiny constant. You just take baby steps along the direction of the minimum. So problem solved, right? We have an algorithm, or do we? So now you can go and implement it. What stops you?
Well, I have to wonder, I mean, like this, you're looking for the coefficients of a linear regression model, and this is already, there's already an analytical solution to this.
Yes.
You can get the answer exactly, so why?
Why bother? This is just as to introduce the idea of gradient descent. You can get the answer analytically, obviously, and that only works for this kind, some special functions. Very often, in fact, the next objective that we'll see, we can't get the answer analytically. So, what is left? What do we still need to do?
Calculate the gradient.
Calculate the gradient. But you know calculus, so you can calculate the gradient, right? Let's work it out. So, we need to find out so I want you to first convince yourself that if I tell you how to find the gradient, you should be able to implement this algorithm. Because this here is a vector subtraction, this is just subtracting one array from another, and that's it. So all you need is to find the gradient of the. So the gradient of an n-dimensional function, of a function in, from Rn to n, will have n components. It will produce a vector, and all we need to do is to define what is to derive what the jth element of that is. Just as a reminder, W is a vector with d dimensions. So we need to find a d-dimensional gradient. let's see how that works. And if you're not comfortable with vector math, I'm going to try to step through this a bit agonizingly slowly. We want to find the derivative of this function j with respect to this function capital J with respect to the, now I notice that I'm using same letter with respect to the jth element of the weight vector. So you have a W which looks like W1, Wj, and we want to find the derivative of this function with respect to Wj. But the function is simply, so is of this function which is just this. And this is a fairly simple thing to do. It may look complex. Let me work out this thing. So the derivative of this is the derivative of the sum is the sum of the derivative. No shock. Or you guys are very quiet, so utter shock. Now this is just that we have a function that's a square, so it is half 2 times the derivative of that inner thing. The same thing here. Right? So all we need to, by the way, the question somebody asked, why do we have a 2 so that it gets cancelled here? That's why. So the derivative of this, so all we need to do is find this guy, derivative of this thing. But W transpose Xi is simply the sum of all the things. So it is that's a big summation. But there's only one term here which has a Wj, which is this guy. All the other things vanish. So this guy is just minus X. Okay. So let me clean it up. Any questions about this? Let me clean it up and I'll step through this again so that you don't have to deal with my handwriting. So the derivative of the sum is the sum of the derivative. And the derivative of the square, we know how to do it. We keep applying the chain rule. This is the big thing here. We keep applying the chain rule and do it for every dimension. And we keep, and now we have the derivative of the whole function, and this is the jth element of this whole thing. One element in the gradient vector. Questions? So the last thing I want to say today, and I'm going to pick up from here again, and if you're confused, what you should do is work out this math yourself. The derivative has the following property. It's the sum, it's the sum of the overall examples of the error, of the actually magnitude of the error times the input. And this similar sort of an observation where the derivative of your learning objective ends up being a function of how much error is there and what is the jth feature. So I'm going to continue on this tomorrow or in our next lecture, and we'll pick up from this gradient descent and continue the algorithm. A reminder, I have office hours after class today, so if you have questions, just show up. And you know, the usual things about projects and homework 1.
Stop screen.